Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're solving examples considering buckling in columns. Next example is a problem from Mechanics of Materials by Timothy Philbott, Wiley 3rd edition. The problem statement reads, rigid beam ABC, shown here, is supported by a pin connection at A and a 180 by 180 millimeter square timber post that is pin connected at B and D as shown. This is our timber post here. The length dimensions of the beam are x1 equals 3.6 meters. Let's note that, 3.6 meters. x2 equals 2.8 meters. Let's note that. The timber post has a length of 4 meters, so L equals 4 meters, and an elastic modulus of E equals 12 gigapascals, given E equals 12 gigapascals. The factor of safety of 2 with respect to buckling is satisfied. Factor of safety equals 2 with respect to buckling. And we're asked to determine the magnitude of the maximum distributed load W that may be supported by the beam. So we want to find a W allowable, and given the units, meters, let's find that in kilonewtons per meter. So our working units for this problem, it makes sense to consider, since E is given in gigapascals, and we know a stress, kilonewton is a gigapascal is a kilonewton per millimeter squared. Let's, at least for the start of the problem, our working units will be kilonewtons, millimeters, and gigapascals for calculating the stress and the critical buckling load. Okay, our approach to this problem is that we want to consider the allowable load in this column based on buckling considerations. So we can calculate a critical buckling load for pin-pin support conditions and the allowable load based on a factor of safety of 2 with respect to buckling. And then based on a free body diagram of the beam section where the load in the column would be considered a reaction in the beam and transfer that load into the beam, we can then calculate the allowable load that would equate to allowable force in that column. Okay, so our approach here, we'll find P crit first, P crit being pi squared EI over L squared. And in this case, our cross section we said was 180 by 180 millimeters square. So it looks something like this. 180 millimeters, 180 millimeters. And so we can see that since it's square, the moment of inertia is the same in each direction. So we'll just calculate it as I equals BH cubed over 12, where B and H are both 180 millimeters. 180 times 180 cubed over 12, and that computes to a fairly large number, which I'm going to write as 87.5 times 10 to the 6th millimeters to the 4th. Not going to carry too many significant digits there. Okay? Critical buckling load, pi squared E in gigapascals, 12 gigapascals, times I in millimeters to the 4th, 87.5 times 10 to the 6th millimeters to the 4th, divided by the length, and we need the length in millimeters, so convert the 4 meters to 4,000 millimeters squared. Okay, so and I compute, that computes to 648, and my units are going to be kilonewtons, okay, because I have a gigapascal, which is a kilonewton per millimeter squared, and then therefore millimeters to the 4th will cancel with the millimeters to the 4th. So 648 kilonewtons is P crit. With a factor of safety of 2, my allowable stress, P crit over 2, is 648 divided by 2, or 324 kilonewtons. So that's the allowable load on the column. Okay, so going to a new screen, we know the allowable load is 324 kilonewtons. Now we want to find the allowable W, distributed load, over the top. So as mentioned earlier, I'm going to do a free body diagram of this member. Okay, I know that my reaction, P allowable, is going to be transferred to the beam right at that location. And then I know that I also have the W acting on the beam. At the pin support, I'm going to develop a reaction AY, AX. We can see that that's going to be 0. Let me know my distances again. 3.6 meters, 2.8 meters. And the total length of the beam is 3.6 meters plus 2.8, which is 6.4 meters. Okay? So it turns out all I need to do is find the relationship between W and P allowable, and I can do that by summing moments about point A. I don't need to find A sub Y. Sum the moments about A, set them equal to 0. I'm going to take moments positive in the counterclockwise direction. I have P allowable times the distance, distance from A, 3.6 meters, minus my W times the total length of the beam to give the total force, times the length over 2 to get the arm. I just like to abbreviate this as WL squared over 2. So W times 6.4 meters squared over 2. Set that equal to 0. Now I can solve directly for W. W equals, it's going to be P allowable times 3.6 meters, then bringing this over times a 2 divided by 6.4 meters squared. Substitute P allowable, which I found earlier, 324 kilonewtons, times 3.6 meters times 2 divided by 6.4 meters squared. That computes to 56.9, and the units are kilonewtons. This meter cancels this, we're left with kilonewtons over meters. So 56.9 kilonewtons per meters, which is the units we were looking for. So that's a good sanity check. And that concludes this example.